Again, here's the list of all the topics that are in this chapter. 16.0 covered, it was a brief review. This one is very, very short. I'd like you to take this in little chunks. There's a lot of information here, but if you take it in pieces, take some time to think it through, you'll be really far ahead in the long run. Okay, so what do we have here? We have something that are called Arrhenius acids and bases. Back in 1777, Lavoisier, he proposed that oxygen was essential in acids. Humphrey Davis in 1808, when he dissolved HCl in water, it gave an acidic solution. But HCl does not have any oxygen, so they concluded oxygen was not needed. Now, in the old days, I would be in the classroom with you, and before things had to become so politically correct, I would bring lemon juice and laundry detergent. And I would ask for some volunteers, to taste these things. Well, everyone in the class, if someone tasted lemon juice, oh, did they ever make a face? That is the taste of an acid. Now, again, political correctness. I can't do this anymore, but I would have laundry detergent. I'd say, anybody brave enough to taste this? And oh, the face that they made, that is basic. So essentially, these were first determined by taste before you could really do anything with them, all right? So if we try to get scientific now, Arrhenius, same person from the kinetics chapter, he said acidic behavior was linked to H+. He said basic behavior was linked to OH-. And the thing to remember, hint, hint, multiple choice questions on exams, is Arrhenius is for aqueous solutions only. So these are facts that you just have to master. HCl is called an Arrhenius acid because when it goes into water, it produces H3O+, which is another way of writing H+. Arrhenius bases, those are substances that produce OH- in water, and I need to put water in the equation because that lone pair of electrons on nitrogen, chemistry 1210, plucks a hydrogen off of the water. There it goes. It makes an NH4+, think about the Lewis structures, and it leaves behind an OH-. That is how simple Arrhenius bases are. The thing is, you have to get these definitions straight in your head so that there's 3 different types of things we use. This is the first classification. What else do we have here? Well, just a picture. Again, here is my Arrhenius acid in water. It increases the H+, and H+ can be written all these different ways. In fact, there's 29 different ways to write them. We only concerned about the first 2 in chemistry 1210. What about an Arrhenius base? Well, again, that is the ammonia. It plucks off a hydrogen, and it produces the OH-. Notice we must be in aqueous solution. What else do I have here? Well, talking to you about molarity calculations. There are 2 different ways you can carry them out. Maybe recall from Chemistry 1210, Chapter 4, aqueous solution stoichiometry. If things are 1-to-1, very simple. If things are not 1-to-1, you got to be more careful, okay? I'll talk about method 2 first. Method 1 is M1V1 times M2V2, and again, that's if you have 1-to-1 acid and base. You don't need to convert anything as long as you have the same concentrations in both same concentration units. You can come right out with your number of mLs. As you proceed in science, we tend to think a little bit more deeply about what we're doing. So in method 1, we find the number of moles required. We take the molarity, which is moles per liter, multiply by the number of liters to come up with the number of moles. Then I take the number of moles, I multiply it by 1 over the molarity, so my moles cancel out. I come up with the liters, and I come up with the exact same number by the other method. You can do it either way. There is no right or wrong way. It's your choice. Okay? What else is here? Sound like a broken record. I do this a lot in the chapter. You do need to memorize the strong acids and the strong bases. HCl, HBr, HI, HNO3, H2SO4, HClO3, HClO4. Why? Because anything that is not a strong acid it is going to be a strong base. How to do the strong bases? Oh, not a strong base. Anything that's not a strong acid, it will be a weak acid. Yes, I do need to do these things, make mistakes in here, so you realize it is okay to make mistakes. It is not the end of your life. It is not the end of your career goal. You learn from your mistakes, okay? Strong bases. Group 1A, pull out a periodic table, make some notes on it. Strong bases, they come from group 2A. This begins where the transition metals start. That's how I remember it. These four in group 1A go right down the center. Group 2A, they begin at the transition metal, but if you use this enough, it becomes second nature. Okay, and that's the last slide. Very, very short section. Take time to really master it, learn it, understand it, walk around the room, talk about it. Yes, I'm being silly, but I really want to encourage you to learn.